Alright, so continuing with Lecture 5, Part 2, we'll talk about the attitude of a frame. So the attitude basically just has to do with expressing the frame in terms of the Cartesian frame. So for example, EI can be expressed as, this is by definition of course, a I1 U1 plus a I2 U2 plus a I3 U3. This matrix A you could write as, let's see here, so I mean another equivalent way of saying this would be that Aij is EI dot UJ, right? Okay, so first thing, so I mean, for example, and let me give a kind of silly, generic sort of example. But if we had E1 was A U1 plus B U2 plus C U3, and I had E2 was DU1 plus EU2 plus FU3, and I had E3, my third thing in the frame was GU1 plus HU2 plus IU3. In this case, you can read from this directly. The attitude matrix would be A, B, C, D, E, F, G, H, and then I. There you go. That would be the attitude matrix. Now, if the point is fixed, all right. So if we're talking about the attitude of a frame, say in TPR3, then of course this would be a single matrix of numbers. But if the point is allowed to vary, then what you have is a matrix of 9 functions, and these 9 functions describe how the frame varies from point to point. Okay, so one of the fundamental things to notice about the attitude matrix, and I suppose these things could be recast in terms of the standard theorems of coordinate change, but I'm sticking with sort of O'Neill's approach here. It pays off later when we get to talking about Cartesian equations and so forth. So attitude, let's see here. Although I admit I am curious to go and check how this relates to coordinate change, linear algebra style. Anyway, attitude matrix is an orthogonal matrix. Okay, so so what's that mean? That means that A transpose times A is equal to the identity matrix. Now, my notation for that is simply that A is an element of big O(n). Okay, so those are orthogonal matrices. All right. So, great. How to prove that? Well, pretty straightforward. So let's do it. A transpose A. All right, so that's a product of two matrices, right? So let's look at the ijth element of that. That would be the sum, k equals 1 to 3, of A transpose ik A kj. But that would be the sum, k equals 1 to 3, of A ki A kj by definition of transpose. And then, okay, well, remember what we just said a second ago here. AKI would be equal to EK dot UI, and let's see, what's this other thing here? AKJ would be EK dot UJ, All right. So what then? Huh. What is my next step here? Curious. Well, let's see here. So this would be the same. I think we can rewrite this as okay. Duh. I guess there's two different ways to look at it. One way to look at this would be AKI is the, I guess the best way to look at it is that's the kth element of UI, right? So what we're looking at here is a sum. I don't know how is the best way to explain this, but this is the kth element. So if I look at the UI vector, this is the kth component of it, right? With respect to the, well, it is what it is. That's the component with respect to the E frame, okay? With respect to the E frame, this is the kth component of what? Of uj, right? So if you use that theorem we proved in the last little bit, this is exactly the dot product of UI and uj. Again, this being, I mean, that's not, I didn't want to make that a standard notation, but just understand that we're talking about the components of the standard Cartesian frame with respect to the E1, E2, E3 frame. Like, you know, UI is equal to a sum j equals 1 to 3 of UI dot EJ, right? And, well, those are exactly what? I mean, that's the same as EJ dot UI, which is AJI. Do a little index juggling and you can see what we got here. But of course, we know that that is the Kronecker delta IJ, and thus we've proved the the theorem, because that, of course, is the components of the identity matrix. So there you go. There's the proof that the attitude matrix is, in fact, an orthogonal matrix, which will be important to us. Let's see here. Now, of course, we could look at the examples that I went through, right? So it's probably worthwhile to do maybe 2 of those. Let's see here. I'll do the boring ones. Oh, maybe 3. I'll do 3 examples. All right, so E1, 1 over the square root of 3, U1 plus U2 plus U3, E2, 1 over the square root of 2, U1 minus U3, E3 equals to 1 over the square root of 6. Now you could ask, why are we looking at these particular frames? I haven't answered that. These are just examples of frames. I haven't said why these frames are interesting. Maybe these frames aren't interesting. I mean, it's just an example. We will give interesting frames as we go on later. Anyway, so with this frame in mind, the attitude matrix A is just 1 over root 3, 1 over root 3, 1 over root 3, 1 over root 2. There's no E2 component, so it's 0. Minus 1 over root 2, and then here 1 over root 6, minus 2 over root 6, and 1 over root 6 again. And you can check that A transpose A is equal to I. You can check on that, it's true. So there's my example. It's actually my example 2.13 if you're keeping score. My next example is totally boring, but I think it's important. So the next example is just the Cartesian frame. Cartesian frame, you got E1 equals U1, right? E2 equals U2. And E3 equals U3. So that gives me the attitude matrix 1 of the U1s, 0 of the U2s, 0 of the U3s, and then this is 0, 1, 0, and 0, 0, 1. So the attitude matrix of the Cartesian frame is just the identity matrix, which isn't particularly surprising because the whole idea of the attitude matrix is to compare to the Cartesian frame and make conclusions, I suppose. Now, both of these are global frames. They're constant in the sense that if you think of the point P as varying, well, it's saying it's the same attitude at each point in space. It's kind of, I guess it's kind of boring. I don't know. Here's a slightly less boring example. The polar coordinate frame, right? So you got cosine theta U1 plus sine theta U2. E2 is minus sine theta U1 plus cosine theta U2. E3 is the, let's see here, E3 was of course U3. This together gives me attitude matrix. So what it is it's a 2 by 2 rotation matrix, right? With a 1. That just indicates that, well, Z is really the axis of the rotation, if you want to think of it as a rotation on R3. But there you go. And of course, this attitude has a point dependence. If you, vary theta, you vary the frame. You vary the attitude. The attitude has functions in it. Change in those functions describe the evolution of the frame from point to point. I've also, of course, taken the liberty here of expressing the attitude in terms of polar coordinates, right? If you were to express this in terms of Cartesian coordinates, it would not be as pretty, right? It would be like, what you got? You got x, y, 0, minus y, x, 0, 0, 0. I guess I could write this as the square root of x squared plus y squared, right? And then 1 over square root of x squared plus y squared right here, just to put the sine and cosine in terms of Cartesian coordinates. You could do that if you wanted. I don't know why I wrote it. Oh well, what's done can't be undone. So there's some examples of frames. And that brings us to our next topic, which of course is the calculus of vector fields along curves. Now really, this is probably very much the same as what you saw before. I mean, something's a little bit new here, I think, though. So let's just give some definitions. So first of all, we're thinking about the usual thing, a parametrized smooth curve into R3. All right, and sometimes we'll write the curve in terms of its components. So that would be, we could write that as like alpha 1, alpha 2, alpha 3, like that, if we want to think about real valued functions. And then we want to talk about a vector field, okay? So y would be something like a sum over, say, I of y upper I, partial I, all right? Shorthand if you don't mind. So this would be a smooth vector field, but we're really only interested in the vector field near the curve, the image of the parameterized curve, if you like. So we're going to assume that this is an element of the vector fields along alpha. And what all that notation means is that the formulas for the vector field are defined near the curve, and they're smooth. Okay. So in particular, what that tells me is that these component functions of the vector field y sub I, they're defined for some subset of R3. That subset includes the curve, right? And these are the so-called Cartesian component functions of y, of the vector field of y sub I. Then, well, not of y sub I, they're the Cartesian coordinate functions of y. You also have reason, and let me just draw a picture. So, got goodness, the curve could look something like whatever. And then maybe U is just some kind of, you know, like you could think about it like some kind of fuzzy tube, even, that's, you know, like around it. So anyway, you know, it's some open set which contains the curve, right? It contains the curve, and the vector field smooth on that open set. All right, whatever. And so what actually we're interested in terms of defining derivatives on the vector field is y composed with alpha. Okay, so y, if you feed alpha into y, then you get something like sum I equals 1 to 3. What that means, of course, is y sub I composed with alpha. You know, to be explicit, partial xi at, well, oh goodness, I guess I owe us a time dependence, but I'll just say at alpha for the moment. Okay, so for example, an example, good example, well, I don't know if it's good, but it's an example. Alpha of t, and you know, I'm not assuming anything about arc length parametrized or not. It could be anything. I mean, here's the twisted cubic, one of my favorite examples, and here's a vector field I made up. Y equals to x squared partial x plus y plus the sine of z partial z. There's a vector field. Clear enough that this has smooth component functions on all of R3, so in particular it has smooth component functions on a sum set containing this curve, obviously. Identify for this one, right? For this here, we have y1 is x squared. We have y2 is identically 0. We have y3 is y plus the sine of z. Okay, so those are the Cartesian component functions of the vector field. Then the, I forgot to tell you what these things are called. These are called the, I gave them a name. I said that these are the parametrized components. I don't know if other people give them a name or not. I'm going to give them a name. Parametrized components of y along alpha. It's kind of an awful name, but there it is. So what are the parametrized components of y along this alpha? Well, let's see here. So we get y1 composed with alpha of t is what? Well, x squared. All right. What is the x of the alpha of t? It's just t. So that's actually just t squared. This one's easy enough to do. So y2 composed with alpha of t is 0. And this one, y3 of alpha of t is, well, it's whatever we have for y, in this case t squared. And let's see, what do we have for z? We've got t cubed, so plus sine t cubed. So there you go. These are the parameterized components of y along alpha for my example. And so once we have that, then we can do things like define the derivative of a vector field along a curve, or the second derivative of a vector field along a curve. I'll just calculate them here before I even make the definition, and I think you won't be surprised. So y prime of t, and I mean, it's kind of sketchy notation in the sense that there's no explicit alpha dependence here, but you have to understand that y prime of t only makes sense with respect to a curve, which has to be given in terms of context or something, okay? That's, you know, that's how it goes. So we got t squared, and I'll write it obnoxiously for a second here, partial x at the point alpha of t. And then plus 0, right? And then plus parentheses t squared plus sine t cubed. Oops, I haven't differentiated anything, have I yet? I'll fix it. it's waiting in the marker, sorry. Partial z at the point alpha t. Alright. And, okay, so I obviously, that's just y of alpha. Oops. I guess the easiest way to fix this is just to say composed with alpha. Scratchy, scratchy, scratchy. Of t. Alright, so y prime of t, the alpha goes away, that's our notation, and it's like, so it's 2t. And I prefer to, well, I mean, I guess I could still write partial x of that, but I just like to write u1. And then plus 2t plus chain rule, so 3t squared cosine t cubed u3, right? I mean, okay, fine, just get it out of my system here. I could write that as partial x at the point t squared t cubed plus 3t squared cosine t cubed partial z at the point t squared. If I just really want to write more, I could do that. Okay, true, fine, great. And okay, so what would the second derivative of the vector field y along the curve alpha be? Well, y prime prime of t would be 2u1 plus parentheses 2 plus O product rule. Let's see here, so that's 6t cosine t cubed minus 9t to the fourth sine t cubed. My apologies if I made some stupid calculational mistake in here. That would be typical of me. But there you go, the second derivative. So basically you just differentiate the parametrized component of the vector field along alpha to calculate the derivatives, all right? That's how we calculate the derivative along a vector field. Just to be annoying, I will define it carefully. All right, so definition. If alpha from I to R3 is smooth, parametrized curve, and if you got a vector field y, which is defined along alpha, then y prime, and in fact y prime prime, and so forth and so forth and so forth and so on, yk even, are also vector fields along alpha defined by, let's see here, well, I'm not sure they're, okay, are they vector fields along alpha? I guess I don't technically know those exist in an open set or something, so this is an abuse of language, alright, fine, but anyway, here it is, y of j, let's see here, t would just simply be the sum, let's say I equals 1 to 3 of the jth derivative of y I composed with alpha of t with respect to t, and then of course partial x I at alpha of t. Okay, that's what it is. So definitely for each t, for a fixed t, it is an element, and this is, I mean, there's no debate about this. That is an element of the tangent space at alpha of t, R of 3. I suppose the question is it fair to say that the assignment of these along the curve can necessarily be extended to a larger vector field, which is smooth on the open set containing the curve? I mean, anyway, that's a question you can ask. But I don't think we have the, well, this is not the time to answer that question, let's just say that. All right, so, all right, so that's the definition of a derivative of a vector field along a curve. So some not altogether unsurprising properties. If you differentiate a linear combination, oops, times z, let's see, of two vector fields, you have linearity, okay? For constants, C1 and C2. Also, here's 1, 2, 3. So I think you know what comes next. The derivative of a dot product of two vector fields along a curve. So to be pedantic, this is at alpha of t, all right? Well, that's equal to dy dt dotted with z of alpha of t plus y of alpha of t dot dz dt. I mean, these dot products are taking place. This is the dot product in the tangent space at alpha of t to R3, okay, which we talked about earlier in this lecture. And then finally, you also have the derivative of a cross product. Now we will be using these probably without so much as an attribution to this proposition, which is 2.3.5 in my notes. Now the proof, I'm going to write it as y prime if you don't mind. The proof of these, of course, of alpha of t, pretty straightforward. Really just the same as the Calc 3 proofs, so not sure I really want to do them. I will, let me just show you one and then I'll move on. So, actually I'll prove two. Oh, I got two in the notes, let me do three. So, suppose y composed with alpha of t, all right, is actually equal to a sum over I of, let's say, a upper I ui. And let's let the notation for z, the component functions of z, let's call them b, all right? Okay, so then the cross product of these two guys, y, and I guess I'm missing a of alpha of t up here. I am missing that in the notes too. Oh well. Yeah. All right, so y cross z of alpha of t, right? That's this thing cross that thing, right? So, but well, those are Cartesian coordinates, so the formula is simply sum over k of ai bj epsilon I jk uk. So if I differentiate this, well, I'm differentiating a vector field, right? But the differentiate a vector field is to differentiate its components. These are constants, so they just ride along. And what you have then is y cross z prime is equal to sum. I drop the alpha because that's our notation, okay? Annoying as it is our notation. And so I have ddt of the product of these two functions. Remember, ai and bj are actually functions of t along the curve. And I pulled out the constant epsilon I jk. And of course this is sitting here. That's the definition of the derivative of the vector field. Almost the definition. I pulled these constants out. Alright, fine. Then the product rule gives you that this is dai dt bj plus ai dbj dt. Plug that in there, distribute the sum, and voila. You've got yourself a y prime cross z plus y cross z prime. Right, and it's just from the product rule on that expanded out. It's really just that. So, by the way, I mean, again, it's just the hero here. If you'll allow me some MasterChef terminology, the hero really is it's that Levi-Civita symbol. The notation just fantastic. All right, so anyway, and there you go. I was greedy. I defined up to the kth derivative, so there they are. I've only given you properties for the first and second, the first derivatives, but there are, in fact, properties for second or third derivatives. There's like a binomial formula expansion that's good for that. And I'm not sure what happens here exactly, but there's got to be some sort of identities for higher derivatives. Yeah, whatever. If we need them, we'll find them. Okay, so finally, almost done with this lecture that seems to have no end. A theorem. All right, so I guess, what do we mean by parallel? Well, is this parallel to this? I would say yes, right? But you notice we've got some kind of y. I mean, this vector's down here, right? This one's up here. So how can I compare them? Well, I compare them by parallel transporting, right? Maybe it's over here. So the parallel transport, I have to maintain the direction and move the point of application up so they match. And if you do that, and then they match, then you're good to go, right? They're parallel. But I wouldn't assume that they have to have the same, same length. I mean, for me, I would say that these two are parallel. Oh, I'm sorry, assuming that that's the direction. So that's the direction, all right? So if they have the same direction, even if they have different lengths, I would say that they're parallel. And distantly parallel if they have different points of attachment, but basically if you just drop the points of attachment and then just look at the vector parts, right? If the dot product of the two vectors is just equal to the product of the magnitudes, that says the angle between them 0, and to me that would say that they're parallel, distantly parallel if they have different points of attachment. Fine, all right. Okay, so that's their theorem. Let alpha from I to R3 be a smooth curve. Smooth parametrized curve. Then we have a couple statements. One, alpha prime equals to 0. If and only if alpha of t is equal to p for all t in the interval of the domain of definition for the curve. In other words, the curve is really just a point. 2, the alpha prime prime is equal to 0 if and only if what? Well, if and only if alpha of t is equal to tv, oops, I wrote it backwards, plus p for all t and I for some v in R3, okay? And 3, and of course this is to say that alpha is a line, right? We can recognize that parametric equation is the equation of a line with direction vector v and base point p. If we have y a vector field along alpha, right, then the derivative of y prime is equal to 0 if and only if, well, y composed with alpha, and I'm just giving some notation here, which we're going to say is C1 U1 plus C2 U2 plus C3 U3. That makes C1 C2, oops, C1 C2 and C3 functions, right? But actually not for constants. Well, I mean, constant functions are still functions, they're just kind of boring ones. C1, C2, and C3. All right. So there's the theorem. All right, so how do you prove these sorts of things? Well, without much effort, actually. So the proof, I will just say this. The converse direction, right? The converse direction for 1, 2, and 3. You just differentiate, right? Differentiate this. If that's given, alpha prime is 0. Differentiate this. If alpha is given like this, you differentiate twice, you get back alpha prime prime is 0. Okay, great. if I have that the parameterized components of y along alpha are c1, c2, and c3, and they're constants, if I differentiate it, it's 0. Okay, so basically I would argue that that direction of the biconditionals is immediate from differentiation. Okay, and the definitions involved. Okay, so let's look at the other direction for 1. So suppose alpha prime equal to 0. All right, what's that mean? So let alpha equal to alpha 1, alpha 2, alpha 3. All right. Oh, did I forget to define something? Oh no, I sure did. Oh, I'm sorry. Well, funny. Okay, so a definition is in order. Sorry. This is the, what? Velocity, right? This is the acceleration. So, alpha prime of 0, let's see, I defined it back over here. Actually, did I even define it? No! Oh no. Maybe I defined it in the previous chapter. Oh no, oh no. Well, basically just following the, well, let me just define it. Alright, fine. It's really not that surprising. Alpha prime of t is the sum I equals 1 to 3 of d alpha I dt partial xi at alpha of t. Alright, and alpha prime of t is exactly alpha prime of t. And that makes sense because if I define alpha of t like alpha prime of t, it gives me a vector field, right? Ignoring that little bit about open sets around the thing, which I never really do anything with. But if we were being more careful, we would. Anyway, so if that's a vector field, then I can differentiate it along the curve alpha, right? And that would be the alpha prime. Or if that's still unsettling to you, all that amounts to, of course, is sum over d squared alpha I dt squared partial xi at alpha t. All right, so there you go, acceleration and velocity. So suppose the velocity is 0, right? If the curve has these components, then the condition that the velocity be 0 amounts to the condition that d alpha j dt equal to 0 for j equals to 1, 2, and 3, right? Now, it should go without saying, we assume, it is universally the case in my notes, all right, that when I talk about the interval of, we assume that I is connected, okay? In other words, it's either a closed interval or a half open, half closed, or a ray. Anyway, it just has one connected component, all right? So since I is a connected set, all right, if you have a derivative is 0 on a connected subset of real numbers, it follows that alpha j is just equal to a constant. Let's call it c sub j. All right, but let's see here. However, we also, well, I guess we don't know anything yet. What do we know? We're assuming alpha prime is 0. I'm trying to think of how I know. Oh, I'm sorry, I'm an idiot. Okay, so that means that, if we say the point is C1, C2, C3, if we say P is that, then there it is. Alpha of t is equal to p for all t. All right. It's really not that complicated. I don't know what's wrong with me. All right, this direction here for 2, almost the same argument, right? If we have alpha prime prime equals to 0, right? That implies that d squared alpha j dt squared equals to 0 for all t and I, which implies that alpha j of t is equal to like cj times t plus, let's say, I don't know, well, whatever, Pac-Man sub j, all right? And so just identify cj as the point, as the v, and let's see here, Pac-Man as the point p, so that with that notation in hand, we have alpha of t is tv plus p, which shows that alpha is a line, which is what we set out to show. Second derivative of the acceleration being 0 implies that you have a line, provided that the v is not, provided though, of course, that this v is not 0. If the v is identically 0, we could have a point again, all right? But if we had that the curve was a regular curve, right? A regular curve has non-vanishing velocity. Certainly, it's an honest-to-goodness line. And then finally, the last implication for 3. What do we have? We have y prime equals to 0. All right. So let y composed with alpha j, let's let that function be, how about a upper j, all right? So if I have y prime equal to 0, that means we have daj dt equal to 0 by definition of a derivative along a curve. All right, but then I can integrate, right? Hence, a sub j, a upper j is actually equal to a constant, c sub j for all t and I, which then tells me, of course, that y is just equal to like c1 u1 plus c2 c2 u2 plus c3. I keep fighting with my components being up. It does matter in this course. I will try to put them up when it's helpful. But admittedly, I am using a slightly hybrid notation on that point. I will admit that. All right. Now here's the thing. I kind of disagree with O'Neill a little bit here on something he says. I'm just going to read a paragraph from my notes here just right quick. If we had that y, a vector field along alpha, had constant length, then I do think we do have the equivalence that, so if y has constant length along alpha, let me write it out. If the length, if y of alpha of t, right, if the norm of that is constant, right? Or if, in other words, if I had the derivative of this was equal to 0, that would give me that the length of y was constant along the curve. Then I think I could say, if this was given, then I think I could say this. I could say y prime equals to 0 if and only if, what? If and only if y of alpha of t1 is equal to y, well, not equal to, but scratch that, distantly parallel to y of alpha of t2, all right? But if I don't have this condition, then it seems to me I could have some curve, right? And how can I say this? I could have vector fields which are parallel along alpha but have variable length. And then I give an example in the notes. So right here I say, you know, if I had y of alpha of t, if I had just the line, say TTT, for 1 to 2, and I take the vector field y as xu1, then y of alpha of t is tu1, right? So pretty clearly the length of y of alpha of t is not constant, it depends on t. But on the other hand, certainly t1 for t being positive is definitely distantly parallel to u1, right? But y prime is not 0. In fact, y prime is u1, which is not equal to 0. So what I'm trying to say is that lemma 2.3 on page 56 of O'Neill is false unless we insist y have constant length. But you know what? Where he uses it is like on the Frenet frame, which is the next thing we're talking about. And the Frenet frame are exactly those kinds of vector fields which are constructed to have constant length. So my my grumbling about the comment about distantly parallel vector fields in lemma 2.3 is it's kind of a moot point. All right, anyway, so there you go. We will pick back up in lecture 6 about the Frenet frame along a curve. Thank you.